Recall from lesson 4.8 that the complex numbers a plus bi and a minus bi are conjugates. Similarly, the irrational numbers a plus the square root of b and a minus the square root of b are conjugates. If a complex number, or an irrational number, is a root of a polynomial equation with rational coefficients, so is its conjugate. Take note, theorem, conjugate root theorem. If p of x is a polynomial with rational coefficients, then irrational roots of p of x equals 0 that have the form a plus the square root of b occur in conjugate pairs. That is, if a plus the square root of b is an irrational root with a and b rational, then a minus the square root of b is also a root. If p of x is a polynomial with real coefficients, then the complex roots of p of x equals 0 occur in conjugate pairs. That is, if a plus bi is a complex root with a and b real, then a minus bi is also a root. Problem 3. Using the conjugate root theorem to identify roots. A quadratic polynomial, p of x, has rational coefficients. If the square root of 2 and 1 plus I are roots of p of x equals 0, what are the other two roots? Well, since p of x has rational coefficients, and 0 plus the square root of 2 is a root of p of x equals 0, it follows from the conjugate root theorem that 0 minus the square root of 2 is also a root. Since p of x has real coefficients, and 1 plus I is a root of p of x equals 0, it follows that 1 minus I is also a root. The other two roots are the negative of the square root of 2 and 1 minus I. Your turn. A cubic polynomial p of x has real coefficients. If 3 minus 2i and 5 halves are two roots of p of x equals 0, what is one additional root?